autoencoders and a bit of generative AI. So this is the last part of the course, and it's a very brief introduction to the idea of how you can generate data, and this is what we have in deep generative models. So pretty much what you have learned in this course is just the computational toolbox that you can use when you want to generate data, but of course you need to have some statistical background there as well. Well, it has its own lecture, its own course, so we are just going to get the idea, okay? So first thing, what we want to do, we want to first start with autoencoders. There are very good computational modules, which is basically encoder-decoder architecture for unsupervised learning that we had before, but the problem just a bit changed. And then after that, we're going to get a bit of idea about what generative AI is and how we can actually generate new data samples, say, out of noise, right? So yeah, generative AI, as I told you, it has its own course in summers. We had it first time this summer, so the next summer we're going to have it again, hopefully. And then we're going to talk about autoencoders first. Let's start with the autoencoders. So what is the idea in autoencoders? Well, let's consider this super simple example. I have this data set, and the samples inside this data set, x's, are two-dimensional vectors, okay? Every single xb that you have inside this data set is two-dimensional, okay? It has only two entries. What I want to do, I want to just reduce the dimension, like this vector, into a smaller dimension. It means that I want to get this two-dimensional vector and compress it into, for example, one-dimensional number, right? So what I would do, I just think of the most simple kind of compression. So I get my sample xb, I multiply it, I compute the inner product with one vector of weights. So basically I have two weights, they get multiplied with the corresponding entries add up, right? Just like a basic neuron with no activation, right? So I get this guy, this is now a scalar, right? This is lower in dimension. So if I had two-dimensional vector, I can get now a number, right? So I get this number as the compression, and next what I do, if I want to decompress that one, so if I have the number z, and I want to get back to my signal, I just find another vector, w hat, which is again two-dimensional, gets multiplied by z, takes me back to my signal, right? To my, vector, right? So I started from x, compressed it into z, then from z I get back to the x hat. Everybody's cool? Quite simple problem, right? So I want to do that, and can I do this in general? Well, it depends on x, right? How does it look like? You cannot necessarily do that. So let's start with just writing down the problem based on what we have learned in the course. So if we want to find these weights, w and w hat, what would you suggest to do? I need to write down a risk function, right? Find out what is the best kind of risk function that I need for this compression problem. Then I find out what are w and w hat, the best choice of them, right? To do this for me. So I'm going to do that. I would say, let's just write down things compactly. I would say, okay, say I have b different samples inside my data set. So every single sample x1 to xb is getting multiplied with the same weight, right? With the same weight vector w, right? Once it got multiplied, then I have b different version, compressed version of them, right? z1 to zb, these are the compressed versions. And now if I have this guy, first of all, I can write down this guy in this compact form. So I can take w out. Now I put all the samples inside one matrix, right? X is the big matrix. The first column is the first sample, second column the second sample, and so on. I multiply that weight into this guy. I'm going to get the whole pack of my compressed samples, right? Now, I have these compressed samples. I want to get back from my compressed samples to original samples. What does it mean? It means that if I get these compressed samples, z1 to zb, if I multiply every single of them to the decompression vector w hat, I should get back to what I want, right? So this means that these x hat 1 to x hat b should be exactly x1 to xb if I want to have perfect compression. Everybody's cool? Now, again, I can write this guy compactly, right? I can take W hat out, right? So W hat comes out. And then I have Z1 to ZB. And this pack of compressed guys we already computed here, right? Z1 to ZB is basically the weight, the compression weight multiplied with my whole data samples, right? So this is what I get. So this is what I decompress, X hat. This is the decompressed version of my data set. And this X is the original data set. And the way that they are getting connected is multiplying the decompression vector to compression vector, which makes sense, right? Now, just a quick hint here. Z1 to ZB, what is it? It's a vector, right? Every single Z is a number, right? So it's a vector. It has B different columns, right? It's a row vector. And now, you have this row vector. You're writing it down in this form, right? This W is a two-dimensional vector, right? And this matrix X is 2 by B, right? It means that it has like is a stack of B different vectors, right? And all of them two-dimensional. Now, same thing is happening for X hat. So X hat is the same thing. Now you just tell me what is this guy, W hat times W transpose. All of this, which is getting multiplied by X. Is it a vector? Is it a matrix? What is the dimension? W hat is a vector, a column vector, right? W transpose is a row vector. What is it? Matrix. What is the dimension? 2 by 2, right? You see it, right? Everybody sees that? So W hat times W, it's going to make you 2 by 2 matrix. That 2 by 2 matrix is multiplied by X, which is 2 by B. It's going to go to 2 by B X hat, right? Okay. I mean, it's not a big deal. Just wanted to make sure like you see it, okay? Great. Now, the point that we want to have is that after decompression, we want it to be exactly like what we had before, right? So this means that I want this X hat to be exactly same as X, right? Now, one question. Do you think that this is necessarily feasible, that I make this X hat exactly like X? Yes? No. Right. Exactly. So we cannot necessarily do that because this W hat times W transpose is rank 1 matrix. It's not a full rank matrix. This means that you can never make it exactly like identity matrix, right? And if you want this to happen, you need to have W hat times W to be identity matrix, right? So mathematically, this is impossible, right? So basically, you have a overdetermined system of equations, which you cannot solve it, right? It has no solution. So if I want to just talk in the ML language, basically what I want this decompression. So this X hat, this guy, W hat times W times X, this is what I decompress to be exactly like X. This means that this difference should be minimized, right? If I want to make it exactly 0, then I need to have this identity, this guy being this one, or in other words, I need to have this identity, W hat times W transpose, to be exactly like the identity matrix, and this thing cannot happen, right? This never happens because left side is rank 1, right side is a full rank. Well, you have less variable than the equations you have, right? So, moral of the story, this guy is impossible because this matrix, rank 1 matrix, can never be identity matrix, okay? But this is true when we think about a very general X, right? But if we don't think about a general X, it might be the case that you can do it, right? How would it be? Let's think about this particular example, okay? I have this knowledge that the samples inside my data set look like this, okay? Well, I don't know what is exactly the sample, but the thing that I have learned empirically or out of some extra knowledge I got out of somewhere is that the first entry of the vector is 2 times the second entry, right? Now, I don't know what are the numbers exactly, but I do know that always the first entry is 2 times the second entry, twice larger. Now, if this is the case, do you think that you can compress this data by only, or represent this data with only single number, single scalar? Can you do that? And what is that a scalar? This is alpha, right? So basically you can do this because every single vector, even though this is 2-dimensional, is just represented by one scalar alpha, right? If you know alpha, then you know the vector, correct? And you can do that. Then you can simply put it inside the formulation that we had. So basically you just say that my compression vector is this guy, for example, right? The solution is not unique. You can come up with any compression and decompression pair. But this is definitely one solution, right? You get the first guy subtracted from the second guy, right? The first entry from the second entry. Then it's going to be alpha, right? And then when you want to decompress, you just get that alpha, you multiply it by 2, 1, right? So you just get alpha, you keep it as the second entry, you multiply it by 2, the first entry, and you're going to get your vector back, right? If you write it down, your z is exactly alpha. That is the compression that you have. And if you decompress, you exactly get back to your data, right? Everybody's cool? Questions? Now, here we can exactly make our data compress into one scalar number and get back to that data, right? Now the question is, here, is this W times W hat, does it get to be identity matrix? No, that never happens, right? We said this is mathematically impossible, right? So why we can do it here? Any idea? Yes?
Well, because the initial number is just, well, as we said, they both depend on alpha d. So.
Right, but if, yeah, that's correct. Yeah, but if you want to think about like geometrically, for example, you would say that if I don't have that information, that the first entry is 2 times the second entry, right? Then this means that I am somehow assuming that my data could be any point in the 2-dimensional space, right? But if I know that the first entry is twice the second entry, what does it mean? It means that any data point that I have is lying on such a line, right? Correct? So this means that I do know that my numbers are here, right? My vectors are here, right? Even though they are 2-dimensional vectors, but they are still lying on a line, right? And a line is not 2-dimensional, right? That is 1-dimensional. The only difference is that I am seeing it in a higher dimension, right? This is still a lower dimensional surface, right? And if I know that, this means that a lower dimensional, a 1-dimensional line needs only one scalar to be represented, right? As long as I do know what is that line, then I can just compress everything by that one dimension, right? Everybody's clear? So the key point here is that the data itself is lying on a lower dimensional space, right? So this means that the data by default is much smaller in dimension as I can see it, right? And this is a dummy example, but in practice, this is really the case. Like if you look at MNIST images, they are only, basically they are only very dark, very light pixels, right? And even though this is 784 different pixels, at the end of the day, probably there is one lower dimensional representation for that image, right? That I could essentially just use that one to represent the image, right? So I can get that image, I can compress it with significantly lower number of pixels, and then whenever I want to get back, I again decompress it to what I need, right? Everybody's cool? You see it? Okay. So do you have idea what is this this problem or this kind of compression problem? What do we call it? PCA, right? Principal component analysis, right? So you have data, a bunch of samples. You think that your data can be represented in lower dimension, right? They are, for example, 100 dimensional vectors, but you do know that, well, there could be some 10-dimensional representation for them, right? And what you do, you basically say that, okay, I assume that I have a linear encoder, a linear compressor. That linear compressor gets multiplied with every sample and takes me to the lower dimension. And whenever I want to get back to my data space, I get a decompressor, which is taking that 10-dimensional representation and takes me back to the data space, right? So that is principal component analysis. You have it in 1513 with details. Why do we call it principal component, or that principal components comes from where they, I mean, essentially you can show that when you think about linear compression, linear decompression, then those matrices are basically the, is containing the compressor and decompressor contain the eigenvectors or eigenvectors corresponding to largest singular values of your data covariance matrix. Yeah? So you do a bit of analysis and you find out that if you know your data, that out of that you can find out what is exactly the best compressor and decompressor, and they are corresponding to the principal components of your data. Because of that, we call it PCA, yes? No, we don't do. We now get to nonlinear one. But the original version was, I mean, old days it was PCA because, I mean, the good thing about PCA is that you don't need any training. So you don't need to find out what is W and W hat. It has a closed form solution. But in practice, you don't need to limit yourself to a linear case. Questions? No question? OK. So PCA is, is described in this form. So I have n-dimensional data points. And what I want to do, I want to learn some weights, W, that's going to take any n-dimensional vector into a lower dimension, say L-dimensional space, right? And that Z representation is what we call it latent representation. Why latent? Because you take from a space which you have feeling about into a space you don't have any feeling about, but mathematically that makes sense, right? Yeah, an image in MNIST image, or eyes can see it, or visual ability can see it, but if I take it into a 10-dimensional space, those numbers probably I have no feeling about them, right? But it's still okay. I mean, it can represent the image, right? That space is the latent space, and the image, or the sample which is representing your particular data there is the latent representation. So you're taking your sample from your data space into the latent space by this latent variable representation Z, and then whenever you want to get back, you get that Z, and then you again decompress it by some linear matrix. And what you hope that after decompression you have minimum amount of error. Like your decompression is as close as possible to your original data, right? And if you solve that problem, then it's going to be the PCA problem. You find out what are those matrices, the compression and decompression one. Now, one thing that you should pay attention here is that we do not have this nice property that everything, for example, lies on a line all the time, right? But in most applications that we do have this property that this thing is somehow happening approximately, okay? This means that maybe the samples are not lying on a line, but they are somehow lying on a very narrow band around the line, right? And as long as I find out what is that line, which is somehow going through that band, then that guy can give me a representation, right? When I get that compression and I decompress, I definitely go back on this line, right? Which means that I'm going to have some compression error, right? But that's okay. As long as the band is quite narrow, that compression is proportional to this, width of the band, right? It's okay. I can handle it, right? If I get a tiny bit of, blurred image after decompression, maybe I am okay, right? Because I simply want to know what is the image, right? I don't care about the quality, okay? So that is not always happening exactly, but this can happen with some approximation, and this is what we do in PCA. Now, we can think about this PCA to be a neural network, and this is the whole thing we had in the course, right? Anything, even the linear transforms, we can think of it as a neural network, right? A network of a bunch of basic computations. Now, let's do it. Let's think of this PCA as a neural network. So how I can think about this, I have my vector. It has x1 and x2, right? x1, x2 are the entries in one data sample, right? And what I do, I compress them by weights, right? So this means that I get x1 multiplied to some weight, x2 multiplied in another with some other weight. I add them up, right? And then this is the compression that I get, right? Now, if I got that compression, how do I decompress? I get that z, right? This z is the compression. Oh, I thought this has the decompression as well. Now let me go here. Then I get back to that one. So I get my z. Out of the z, I want to decompress. How do I do that? I get my z. I multiply it to one weight, w1 hat, on another weight, w2 hat. I get to my decompression, right? This is the decompression that I have at the other side, right? Everybody's clear? Now, if you want to do it higher dimensions, you can do it this way, right? You might have n-dimensional input, right? You multiply it to a matrix. This means that if you have L-dimensional latent space, you have L different neurons, right? Every single neuron has its own weights. It's going to get multiplied to the data sample entries inside the data sample. It computes you one corresponding entry inside the latent space, right? That is the way that you do the compression. And of course, you get that z. Again, you compress it, decompress it by multiplying into a bunch of weights, right? Meaning that you have another bunch of neurons at the output, which is computing your decompression, right? So, now, this problem that we have is an unsupervised problem because I have my data x, but I don't have any label for it, right? Any sample that I have does not have any label, right? I give you a bunch of images. I tell you just find the best compression, right? There is no label corresponding to this compression. Now, how can we solve this problem if we want to solve it in practice? If you, for example, want to train this neural network, what would you take as your loss? Exactly. So you want x and the decompressed version x hat to be as close as possible, right? So you're going to take their difference as the loss, right? And this is exactly what you do always in unsupervised learning. So any problem that you have, it's true that your data does not have a sample, label, but obviously there is a way to make a label for it, right? And this is, for example, here, when you want to do the compression problem. Well, in compression, you don't have label, but obviously you want your data to be as close as possible to the decompression version, right? So if I tell you like this, like I give you a data sample and give me the best compression, well, you're lost because there is no label as a kind of optimal compression, right? But you can say that, okay, I'm going to train my compression together with decompression, right? And when I decompress, I must get back to my data, right? So I'm going to add the decompressor here, and then I would say, okay, I want to find all the weights together, W1, W2, W1 hat, W2 hat, all together, such that x and x hat are the same, right? Now you can train, right? You can just write down the loss, and then you can find all the weights, such that this problem, this loss is minimized, right? Everybody's clear? So your loss would be essentially this guy, right? The difference between what you have sent into the whole architecture and then what you get out of it as the decompression, right? And now you can find W and W hat. Everybody's clear? Questions? So if you have this guy, if you just try to minimize this guy, okay, then you're going to end up with the PCA solution. So you're going to find out that W and W hat are somehow written in terms of the principal components of your data correlation matrix. Okay, but that is not the most important thing right now. The thing that we want to do, we want to look at this guy as a neural network, right? If you look at this as a end-to-end neural network, end-to-end architecture, what kind of architecture is this? Any idea? Did we have this architecture before? What was it? Encoder, decoder, right? So you have one encoder. This is basically encoder, decoder. You have one encoder. It gets your data. It encodes it to the latent representation, right? Then you come to the latent. This is the bottleneck that we had, right? For example, the translator was looking at our tokens, right? It computes some bottlenecks, some hidden information, right? Some attention values, whatever, right? That was the representation of that data, right? The embedding of that data. And then it passed that embedding into the decoder, right? The decoder gets that embedding. It takes you to the label that you want, right? Now, the label that you want is exactly the data here, right? So you get your data, you compress it, or basically you represent it with a latent representation, and then you get back to your own data by decoder, right? So this is encoder-decoder architecture. We usually call it autoencoder, and the term auto simply comes from the fact that after decoding, we want to get back exactly to the data itself, right? Since the output of the decoder and the input of the encoder are the same, you call it autoencoder, right? It's encoding itself, and it gets back to itself, right? Everybody's clear? OK. So now, given that fact that this is a PCA is a neural network, and it's basically solving encoding decoding problem as we had in chapter 7, then the question is that why we should focus only on the linear architectures, right? There is no reason for that. We do know that usually nonlinear architectures even work better, right? And maybe we can go for nonlinear architectures as well here. And it turns out that this is a very important thing here. Actually, it could help a lot. Why? Let's consider this example. So say I'm still working with two-dimensional samples, right? But my samples are not on a line. They are in this form, right? So the first entry is sinusoid. The other one is the cos, right? Now, if you have this two-dimensional vector, what is the key property or what kind of geometry you would see if you plot the points? It's going to be a circle, right? Because whatever the first entry is, if you square it plus the second entry square is 1 always, right? Right? So this means that all the points are lying on a circle, but if I want to do PCA, what does PCA look for? PCA is going to look for one line, which is somehow matching your data samples perfectly, right? And in this case, that line, well, does not exist, right? So this is your circle. The blue circle is where your data samples are, right? Whatever data you have is always on that circle, right? And you're going to see a bunch of those points. And what you want to find out is one line, because you are doing PCA, right? By PCA, you simply have linear encoding, linear decoding, right? Linear compression, linear decompression. This is simply one line, right? And you want to find that line which is perfectly matching your points, right? It doesn't matter how you rotate that line. It's never going to pass or going to concentrate samples around it, right? If it was band, as I told you in the other example, if you had a tiny band around the center, right? There is one line which is matching the best, right? If you make it orthogonal, it would never match, right? There are only a few points close to line, right? But when you pass it exactly at the middle of the band, then every point is roughly close to that, right? So there is one solution for this. But here, it doesn't matter how you put this line, right? However you put it is always close to a few points, and a lot of them are far away, right? So basically, there is no difference between this line or this line for your solution, right? And none of them is a good representation of your data, right? But one question, can you compress the data on this circle by representing it with only one scalar? Can you do it? Yes? What is that scalar? The angle, for example, right? If you know the angle, right, then you can build this data, right? But the only issue is that you can build it non-linearly, right? So it means that if I have this angle, I can basically decompress my data. That angle is enough compression, has enough information about my data, right? Now, if I want to just represent it by a neural network, I can still do it by a neural network. Only I need to activate my neurons there, right? How can I do it? Well, say I have my data point x1, x2. This guy is the sine, this guy is the cosine, and then I'm going to take the first one, for example, right? If I compute the sine inverse, the inverse of that sine, if I just find out what is the angle, I can just get the number, say the angle is this one, right? Theta. So out of this arc sine, I'm going to get theta, the angle of my point, right? And if I want to build that point again, I'm going to pass it through two neurons. One of them is activated by sine, the other one is activated by cosine, and it's going to give me back the point that I had, right? It's the same architecture. It's still encoding, bottleneck, decoding. The only difference here is that I have activated my neurons, right? So it's not anymore linear PCA. It's a sort of nonlinear PCA, right? Everybody's cool? Of course, this guy is more powerful when I have nonlinearity in general. It's more powerful than the linear one, right? Because linear one could be the simple case with linear activation, right? So this guy could potentially give a better representation for my data. Everybody's cool? Questions? Again, in practice, you probably do not have your points exactly lying on a circle, but it might be a kind of topology that the points are around it, right? For example, they are circling around a main circle, right? And then if you find that circle in between, right, that circle which passes exactly in between, then that one is somehow representing your data the best. Okay? Everybody's cool? Questions? So one thing. This guy here, this circle, okay? This circle. Is it a one-dimensional topology or two-dimensional topology? I said topology. I didn't say. Yeah? Is it one-dimensional surface or two-dimensional surface? It's one-dimensional surface, right? But it's not a linear surface, right? Have you heard of manifold? Right? If you have a large dimension, right? For example, 3D space, right? Sometimes the things that you have is a kind of weird curvature in that space, right? But it's thin, right? It has zero thickness, right? That is a lower dimensional manifold in this larger space, right? This means that the points on it can be, like if I take out that manifold, if I take out that curvature and I just, push it completely, it's going to be a plane, right? It's still a plane. If I cut this circle and I just straight it, right? It's a line, right? But the only issue is that the line is somehow twisted in this space, right? So it's a manifold. It's still one-dimensional manifold, but it's in a larger dimension, right? But it's harder to represent it as compared to a simple line, right? So that line is the simplest manifold you can think of, but this one is a bit more complex, right? But the point is that almost all data that you have in practice is always, even though this could be like super duper high dimensional, it's always lying on a super, super thin manifold in the data space. Like the image you have with hundreds of thousands pixels, it can be represented with maybe 1,000 dimensions. Because this is actually lying on a very thin 1,000 dimensional manifold in that huge space, right?